Hello, welcome to 13.6, the normal curve. So there are types of distributions. We're going to talk about distributing data, how it's going to spread out if you were to graph it all out like a histogram or bar graph. There's a rectangular distribution. So everything's the same height. These are all pictures from the book. The next is the J-shaped distribution. This is a J-shaped. This is bimodal, means you have two different peaks. We talked about that before, being bimodal. This next one is skewed to the right. Data's leaning towards this direction, or it's more spread out to the right. This is more spread out to the left. Skew to the right, skew to the left. So in skewed to the right, your mode is over here, and the mean is to the right of that as well as your median. Skewed to the left, your mode is here, and to the left of that would be your mean and a median. Okay, the next one is the normal distribution. This is a curve where it's small on the outsides and works up to be peak on the inside. So you get a curve like that. It's called a bell curve. Okay, so properties of a normal distribution. The graph of a normal distribution is called the normal curve. The normal curve is bell-shaped and symmetric about the mean. In a normal distribution, the mean, median, and mode all have the same value and all occur at the center of the distribution. Now, the empirical rule says that 68% of all the data lie within one standard deviation of the mean in both directions. So, within one standard deviation, 68%. Within two standard deviations, 95% of the data. And within three standard deviations, 99.7% of the data. We talk about IQs. 100 is the mean IQ. If you go out three standard deviations, the standard deviation is 15. So if you go out three standard deviations to 145, so it's 115, 130, 145. From 145 above, that's the genius range. So we're talking about a very small percentage of the people. Z-scores. Z-scores determine how far, in terms of standard deviations, a given score is from the mean of the distribution. So the Z-score is the value of the piece of data minus the mean divided by the standard deviation. So it's x minus mu over sigma. So we're going to find the following Z-scores. A normal distribution has a mean of 50 and a standard deviation of 5. Find the Z-score for the following values. So for A, it's 55. Z is going to be 55 minus 50, because 50 is the mean, over 5, which is the standard deviation. That's going to be 5 over 5, which is 1. So it's 1 standard deviation out. So there's our Z-score. For B, Z is going to be 60 minus 50 over 5. That's 10 over 5, which is 2. Here's our mu, and we have 1 standard deviation, 2 standard deviations. So here's Z equals 2. You're out that far. And for C, Z is going to be what? It's 43. So it's 43 minus 50 over 5. That's going to be negative 7 over 5, which is negative 1.4. So here's your 1 standard deviation. This is -1. Here's -2, so it's going to be right about here. Okay, feel free to pause that. I'm going to move on to the next page. For the next one, we're going to refer to the table in the book. Table, I believe it's 13.7, so I'm going to call this up here. So in your textbook on, let's see if I can zoom out of this. No, try this instead. In the textbook, you're going to see a page like this, a bunch of numbers, has a curve on it, has a bunch of numbers. And the way these numbers read, the number given tells how much area is under the curve to the right, to the left of that value, to the left of the value. So in our first example here, example 2, part A, it says determine the area under the normal curve to the left of z equals -5, -0.5. So what we're talking about is on a curve, here's 0, here's -0.5. We want the area to the left of that. So if you look this up on the chart, for -0.5 will be on this side. This is the negative side. This is the positive. They're all positive values in the table, but the negative side or the left side of the mean. So -0.5. Come all the way down here. -0.5. And this is 0, so there's no decimal after the 5. No number after the 5. So it's going to be 0.3085. So that means that this region to the left of this -0.5 is 0.3085. So again, I looked at this chart, found -0.5, and there's no decimal after, so it's the first column. 0.3085 is the area under the curve to the left of that point. So my finger's pointing to the thing on the board now, not the book. Okay, let's go on to the next problem. This button, okay. So that was 0.3085. Now I'm going to probably need to erase this so it's not going to confuse what's on the book when I look at that at the end of the video projector, document projector. So to the left of the document camera, left of z equals 1. So here we're talking about this curve. Here's 0. So here's 1. We're talking about this region here. What's that area of the region to the left of 1.00? Let's find out. So here's our book. Here's 1. And to the left of that, see how the chart is? To the left of whatever value we're talking about, that's going to be 0.8413. Hopefully let's get this a little closer. 0.8413. Take a look in your book too. 0.8413. So that means the area to the left of the 1 is 0.8413. That's a little blurry right now. Oh, here's the focus. There. Okay, the next one talks about being to the right of 1.00. So in the next one we're talking about being, here's our curve, here's 0, here's 1. previous problem talked about being to the left of that. Now what if we're to the right of that? How do we get that? Well, the total area under the curve is 1. 1 minus this other part is going to be 0.1587. So this region is 0.1587. The region to the right of the 1. To the left is 0.8413. We found that from the table. So to the right, we do 1 minus that value to get 0.1587. The next question is talking about being between negative 1.5 and 2.0. So we're talking about this region here. And one way to view that is to say, okay, what if we did the whole thing from 2 on down minus the part that is from negative 1.5 on down. So we find this value, subtract out that value. Okay, so for 2, it's 0.9772. And for negative 1.5, negative 1.5, it's 0.0668. So that difference is going to be 0.9104. So this answer is 0.9104. And the last problem from this example says, how about between negative 1.75 and positive 1.75? Okay. We want this region, so we're going to look at the region that is 1.75 and subtract from it the part that should be missing, which is the region negative 1.75. Okay, so 1.75. Let's go to 1.7. 1.7. That's 1.70. 1, 2, 3, 4, 5. 0.9599. 0.9599. Now let's look for negative 1.75. Here's negative 1.7. There's 1.70. 1, 2, 3, 4, 5. 0.0401. We'll do the subtraction and we get 0.9198. So the area between negative 1.75 and 1.75 is the area 1.75 and to the left, and then subtract the area negative 1.75 to the left. That's 0.9599 minus 0.0401, and we get 0.9198. Let me erase this, so feel free to pause if you want to write this down. These notes are also available to you. So what conclusions can you draw between city A and city B? The math scores, looks like the average score, the same distribution, but the average score was higher in city B than city A. Okay, to find the percent of data between 2 points, draw a diagram of the normal curve. Use the formula to convert the given values to z-scores. Indicate the z-scores on the diagram. Look up the percent that corresponds to each z-score in the table. When finding the percent of data between two z-scores on opposite sides of the mean, when one z-score is positive and the other is negative, you find the sum of the individual percents. Actually here we're just subtracting based on this table, so we've seen it. Find the percent of data between two z-scores on the same side. Both z-scores are positive or negative. Subtract the smaller from the larger. So we're just doing subtraction. When finding the percent of data to the right of a positive z-score or the left of a negative, subtract the percent between 0 and z from 50%. The way these tables are working out, though, actually I think that instruction's wrong. I feel like we've been doing it. Okay, so let's go ahead and do this last example. Assume that the waiting times for customers at a popular restaurant before being seated are distributed with a mean of 12 minutes and a standard deviation of 3 minutes. Find the percent of customers who wait for at least 12 minutes before being seated. So for A, the z-score is going to be 12 minus 12 over 3. That's 0 over 3. And so at 0, so this is who waited at least 12 minutes. So we're at 0 and above. So that's half of the table, 50% of customers. For B, find the percent of customers who wait between 9 and 18 minutes before being seated. So Z would be 9 minus 12 over 3, negative 3 over 3, which is negative 1. And Z equals 18 minus 12 over 3, 6 over 3, which is 2. So we're looking at this curve from negative 1 to 2. So looking at the values up on the table, 0.9772 minus 0.1587. So from the 2 on down versus negative 1 on down, and we have 0.8185 or 81.85%. For C, find the percent of customers who wait at least 17 minutes before being seated. So it's 17 or more. So Z is going to be 17 minus 12 over 2. That's going to be 5 over 3, 5/3 or 1.67. So I'm looking at this chart like this for 1.67 up that way. That's going to be 1 minus the value going to the left. So it's going to be 1 minus 0.9525. You look that up in the chart. That area is 0.9525. And what do we have? 0.0475. Or 4.75% are going to wait more than 17 minutes. And find the percent of customers who wait less than 8 minutes. That's going to be 8 minus 12 over 3. That's negative 4 over 3, or negative 1.33. So we're talking this region. On the chart, that's going to be 0.0918 or 9.18% of the customers will wait less than 8 minutes. Okay, well, that'll do it for section 13.6. So please let me know if you have any questions, and send me your questions. When we meet online, we can discuss them. Hope you enjoyed this. I know the chart thing may be a little confusing. Take a look at the chart, try to see how it set values, and it's giving values from that value and to the left. You see that value to the left. I'll do it from your perspective. Okay, I'll talk to you guys later. Thanks. Bye.